All right, so here we're going to talk about buffer capacity on page 5 of our Unit 4 Part 2 packet. And this is a pretty quick, simple idea here between all the complex calculations we started with and that we're going to be finishing with. Like the name implies, capacity is the size or kind of amount that you're able to fit. Buffer capacity is the amount of acid or base that can be absorbed or neutralized by a buffer before it's no longer a buffer. So before either the acid or base component gets used up in the buffer. And this is completely determined by how much, meaning the moles, of the acidic and basic components are in that buffer solution. So we're going to talk about this more later when we're talking about how to make a buffer. And it's not really applicable here, but just in general, most buffer solutions, and the best buffer solutions, have large concentrations of both buffer components. Because the more of each component you have, the more stuff you can neutralize. So the more weak acid you have, the more base can be neutralized by that buffer. And remember, in our pH calculations, the amount isn't what matters as much as the ratio that affects the pH. So we can make a very concentrated buffer solution that has a very high concentration of both buffer components that are in the ratio we need to get to a certain pH. So, in general, what we're going to be doing here to answer these questions that are asking us how many grams or how many milliliters of a certain substance could be added to the buffer or to reach the capacity of the buffer, we first need to decide which part of the buffer it's going to react with and then use the moles of that part for further calculations. And so in general, remember, we're going to be dealing with grams or volumes of our buffer components and of these substances that the buffer is neutralizing. So we might need to calculate our moles of our buffer components, and if we have solutions and molarities there, then our moles can be found by multiplying together the molarity times the volume in liters. And then once we're trying to find, if we're asked what is the volume of this solution that I could neutralize, then we're going to have to use the moles we already found to calculate volume again. And that volume will be in liters, and that's just going to be equal to moles divided by molarity. And hopefully we're comfortable enough with grams at this point, getting back and forth between grams, but just in case we need a reminder, if we've got grams given to us, we're trying to turn it into moles to figure out how many moles of something are in our buffer. We divide by the molar mass. And if we then take those moles and we're trying to figure out how many grams of an acidic or basic component we could neutralize, we'll take our moles and multiply by the molar mass to find that number of grams. So we've really just got two problems here, two examples that each have two parts to them. As we're looking at this first buffer solution, it was created by mixing 500 milliliters of 0.100 molar hydrocyanic acid with 2 grams of sodium cyanide. That is a buffer. We've got our weak acid and its conjugate there. And if we want to find it's always a good idea. I know I said we'd start by figuring out which component is going to get canceled out, but whether it's asking for us for the pH or the buffer capacity, a good first step is always to find our moles of our buffer components. So I'm going to turn this into liters and then multiply those together, and that's going to get me the fact that this hydrocyanic acid, the weak acid we're dealing with here, has 0.0500 moles of weak acid present in our buffer. And then I can take that 2 grams of sodium cyanide, and I could do a little bit of dimensional analysis here with our molar mass, which I already did the math, but let me double check what that number is supposed to be. So that's 49.01 grams per mole. Just some quick, normal calculations that we've done a million times there. Gets us that there's 0.04, sorry about that, 0.0408 moles of this conjugate base there combined with my weak acid. So that's going to set the stage for everything that we're doing after this. So if we actually read through part A with this buffer solution, it asks us what volume of 0.5 molar hydrochloric acid could be added to this solution before the buffering capacity is ended. And so at this point, what we need to do is figure out what this HCl is going to be reacting with in our buffer. And because HCl is an acid, a strong acid at that, it's going to be reacting with the base component. So if that's reacting with the conjugate base, then the moles we care about at this point, we don't care about how much weak acid is there. It's irrelevant. We're going to take those 0.0408 moles of weak base, of conjugate base, and that's the moles of hydrochloric acid that can react until we've used up all of that sodium cyanide. So this is the moles of the conjugate base, but that is equal to the moles of HCl that can react before our buffering capacity is over and done with. And so if we're trying to find the volume of that HCl, that is 0.5 molar, all we need to do to find the volume, remember, moles divided by molarity, we're going to divide by that 0.500 molar and get our volume in liters. And there's not much rounding necessary here because we do want to keep 3 sig figs, so that 0.0816 liters is our final answer. If you felt like turning that back into milliliters by moving this 3 times, that would be 81.6 milliliters. But since it didn't specify a specific unit, it doesn't really matter which volume unit we use here. That's our answer. Pretty quick, simple calculations, as long as you understand what it's asking for with that buffer capacity and which component of the buffer we're going to be reacting with. In part B, it asks us what mass of sodium hydroxide could be added to the solution before buffering capacity is ended. Same general question, but here we're dealing with sodium hydroxide, which is a base, so it's going to be reacting with the acid component of our buffer. So we're going to take the moles of our weak acid, which is equal to the moles of sodium hydroxide that we would be reacting with at this point, and we need to turn this into mass, grams. So now we need to do a little dimensional analysis, and since NaOH has a molar mass of 39.998 grams per mole, we basically take our moles times that molar mass, round it to 3 sig figs, and 2 grams is our final answer. That's how much we could add before we break our buffer and we wouldn't have a buffer system anymore. So hopefully this isn't too complicated. This next example is the same situation. We've got a buffer made from 200 milliliters of 0.2 molar formic acid. So if I move my decimal 3 times here as I'm reading through, find my moles of that weak acid there. With 300 milliliters of 0.1 molar potassium formate, that's our conjugate base. Once again, change my milliliters into liters, multiply those together, I get 0.0300 moles of that conjugate base. Part A asks me what volume of lithium hydroxide could be added before we break our buffer. Since lithium hydroxide is a base, it's going to be reacting with the acid component of our buffer. And so we're going to start with our acid component moles, which is equal to the moles of lithium hydroxide we could neutralize. Since it's asking for volume, we take our moles divided by the molarity of lithium hydroxide that we're dealing with. Do that division, get 0.2 out of the calculator, make sure to keep that as a 3 sig fig, 0.200 liters, and that's our answer. And then finally, we've got our what volume of 0.250 molar HBr could be added to this solution before the buffering capacity ends. Because that HBr is an acid, it's going to be reacting with the base component of our buffer here. So that's going to be our conjugate base. And so taking our conjugate base moles, we're dealing with volume again, so we just have to divide by that given molarity of the HBr that we're dealing with. Do our division, make sure to keep the right sig figs, and that's our final answer. So it's really not a difficult process. I know neither of these examples was a basic buffer, But it doesn't matter whether it's a basic buffer or an acidic buffer. If you're adding an acid to a buffer, it's going to react with the base component, whether that is the weak base in the buffer or the conjugate base portion. We kind of simplify that down. They do technically have different roles and do act and react a little bit differently depending on whether it's acidic or basic buffer, but it doesn't change the math and the process that we go through here. So that is our buffer capacity notes. Hopefully it wasn't too bad, and we'll talk about it in class next time if you do have any questions.